Okay, so going over these problems, number 4. So on number 4, we were asked to use the graph to state the value of each quantity. So on A, the limit as x approaches 2 from the left would be 3. On B, as it approaches 2 from the right, it would be 1. And so on C, the limit as x approaches 2 of the function does not exist because the left does not equal the right limit. Then D, f of 2 would be 3. E, the limit as x approaches 4 would be 4. And f of 4 is undefined. So because you have that open circle there, it's actually undefined at 4. However, we can find the limit because it is approaching the same thing from the left and the right. So the limit exists even though it's undefined there. And that one is a removable discontinuity. So questions on number 4? Let's see, and the next even one was 24. Does anybody have any questions on any of the ones up to that through 23? Any of those you want to look at? You're not sure what your question was? Okay, well, this was finding the limit based on looking at the values in a table. So like on 23, it was x approaches 0. So you'd want to put in values from the right and the left close to 0. So maybe 0.1 and then 0.01 and then 0.001. And then from the left, negative 0.1, negative 0.01, negative 0.001. And what you're going to find, if you do that, it looks like it's approaching 0.25. Okay, so 1/4 is what your limit would be on 23. So then 24, same concept. And again, it's x approaches 0. So you're going to put in values to the right of 0. So 0.1, 0.01, 0.001. And same thing with the negatives. Negative 0.1, negative 0.01, negative 0.001. And what you find as you get closer and closer to 0 is that it looks like it's approaching 0.6. So 6/10 would be your limit on 24. 30. 30, we were supposed to determine this limit, and these are infinite ones. So on 30, it was as x approaches -3 from the left. And if you put values in again that are close to -3 from the left, so -3.1, -3.01, -3.001, you find that they just get larger and larger. And so it approaches infinity. And then 38, this one, finding the vertical asymptotes of that and confirming by graphing it. On part A, so finding the vertical asymptotes, well, if you set that equal to 0 and solve, you get x equals 0 and x equals 3/2. Okay, and that is where it would be undefined, right? And usually where it's undefined, that's where you have a vertical asymptote. And in this case, yes, that is where you have your vertical asymptotes. At x equals 0 and x equals 3/2. So any questions on any of these though from 2-2? Okay. Well, let's move on to 2-3 then. Okay, I didn't give you the notes yet. Okay, so now we're finally getting to what I wanted to do the first time. Calculating limits using limit laws. So, and graphs and calculators, can help us out, but sometimes they're misleading, okay? And sometimes we get wrong results in calculating limits. So it's good to be able to solve these algebraically. Oops, I don't think I shared my screen yet. Okay, so going over these laws of limits, the limit as x approaches a of a constant is just that constant. So whatever it's approaching, if we say the limit as x approaches 5 of 10, it's still 10. Okay, so constant is just a constant. Identity, limit as x approaches a of x. Well, that's, as the limit as x approaches 2 of x, it's going to be 2. Okay, so that's the identity. And then a constant multiple. So if I have a multiple in there, so if I have like the limit as x approaches a of 2x, okay, that 2 can come out in front, and it's the same as just taking that constant times whatever your limit actually is, okay? So you can bring constants out in front. Sum and difference, if I have the limit of 2 functions added or subtracted, I can separate those out and find the limit separately and then just add the results, add or subtract the results. Same thing with multiplying. If I have 2 functions multiplied or divided, so the product or the quotient, I can find the limit of them separately and then just either multiply or divide my results, okay? And then power, if I have a power, so like if I have x plus 2 quantity squared, well, I can bring that squared out of the whole thing and apply it after the fact. So in other words, I can find the limit of my x plus 2 and then whatever that result is, square it. So you can bring those powers out. And the limit as x approaches of a x to the n has to equal a to the n, where n is a positive integer. So in other words, if I have x squared, x cubed, x to the 4th, x to the 5th, and so on, any of those, it's just going to be whatever my value is to that power. So if I have the limit as x approaches 2 of x to the 5th, it's 2 to the 5th. Okay, that's what that's saying. And then a root, well, remember a root is really just a power also. So just like the power I can bring out, I can bring the root out. I can find the limit of the function and then take the root of it, the root of the result. Okay, and again, this is where n is a positive integer. So the square root, the cube root, the 4th root, the 5th root, and so on. Now, if n is even, we need to remember that we are assuming that the limit is greater than 0 because we can't take the square root or the 4th root or the 6th root of a negative number. Okay, and then the last one here, the limit as x approaches a of a root. Again, this is like a power, just like if we had x squared, x cubed, etc. Well, this is a square root, a cube root, a 4th root, etc. Whatever it is. If its limit as x approaches 2 of the cube root of x, my answer is the cube root of 2. Okay. And again, assuming that if n is even, our a is greater than 0. Okay. Okay, so to apply these laws, we just have to take the function and try to break it down into pieces that we can apply the laws to. Okay, so that's the idea behind this. So let's just look at this first one. We have the limit as x approaches 5 of 2x squared minus 3x plus 4. Okay, so right away I have some things added and subtracted, right? So I can separate those out and find the limit of each one separately. So I could rewrite this as the limit as x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x plus the limit as x approaches 5 of 4. Okay. And now I can start applying more laws to each one of these separately. Okay. Well, with this one, I know a 2 can come out in front, right? So I can put the 2 out in front. It can be 2 times the limit as x approaches 5 of x squared And this one, the 3 can come out in front. So it's 3 times the limit of x. That's x approaches 5. And this one, well, I'm going to solve this one right away because the limit of any constant is just the constant, right? Okay, so that's 4. Now, this one, the power, okay, and again, you know, there's 2 ways you can do this. You can think about the power coming out in front, but look back up here at this one, number 8. The limit as x approaches a of x to the n, where n is a positive integer. Well, n is a positive integer, so the limit as x approaches 5 of x squared is just going to be 5 squared, right? So this is 2 times 5 squared minus 3, and the law that says if it's just x, it's just whatever I have here, 5 plus 4. So I get 50 minus 15 plus 4. So 35 plus 4, I get 39. Is that limit? Now, and these are, you know, pretty simple examples, but it helps to start with that to see how we break these down. So let's look at this next one. What do you think we would do on this one? What do we do with the quotient? Yep, take it apart. So we can say again, oops, that this is equal to the limit as x approaches -2 of x cubed plus 2x squared minus 1 over the limit as x approaches -2 of 5 minus 3x. Okay. Now, knowing what we just did on the last one, we know we can break this down into each one of those separately, can't we? Okay. So rather than writing it all out, let's just figure out what each one would be. So if I take the limit as x approaches -2 of x cubed, what is that going to be? Is that just going to be -2 cubed, right? And then the next one plus, well, again, the 2 comes out in front, but that just means I take 2 times -2 squared. And then the limit of a constant is just that constant, right? So on the bottom, limit of a constant is a constant, and then the minus 3x, well, that's -3 times the -2. So do you notice here that really what's happening is we're just actually substituting in, aren't we? Okay, and that's one thing that will happen in some of these limits. So we have -8 plus 8 minus 1 over 5 plus 6. So we get -1/11. Oops. Okay, that's our answer. Okay, so questions there. So, and that's what I have a note about on the top of the next page. Direct substitution would have worked in either one of these problems because the function is a polynomial or a rational function. And remember, a rational function is just the quotient of 2 polynomials. Okay, so anytime you have the limit as x approaches some constant of a polynomial or rational function, yes, you can choose direct substitution. Okay. And we can show that this will always be true. So this is what this direct substitution property. If f of x is a polynomial or rational function, a is in the domain of the function, then as x approaches a, f of x is equal to just f of a. In other words, I can substitute in directly. Okay. This doesn't always work when the function is undefined, however, at the limit. So that part that says it's in the domain of the function, that's an important part. You know, if you're dividing by x minus 2 and you say the limit as x approaches 2, I can't just substitute that in, can I? Because I'd be dividing by 0. Okay, so that part of the rule is important. Okay, so strategies here, look for 0 denominators and ways to get rid of them. So maybe you can simplify top and bottom and cancel out that factor that's going to create the problem. Maybe you can rationalize the numerator. And we've heard about rationalizing the denominator. right? It's the same concept. It's just the numerator that we do that to, and simplify. Okay, so look at this one. So finding the limit as x approaches 1 of x squared minus 1 over x minus 1. Well, if I tried to plug 1 in here, it failed, right? I can't do direct substitution because I get 0. It's undefined there. So in other words, 1 is not part of the domain here, is it? Okay, that's one of our restrictions. But if we factor the numerator, so we have the limit as x approaches 1 of x minus 1 times x plus 1 over x minus 1, then we can cancel those. And it ends up being the limit as x approaches 1 of x plus 1. Well, now I can plug it in, can't I? 1 plus 1, the limit is 2. Okay. I probably should have written that down. So we're just doing direct substitution, and we get 1 plus 1, which is 2, because we're just plugging in for the x. And we can separate them out to do that. Okay. Okay, now the new function, so after we've canceled, it is not the same as the original function, okay, but they have the same limit. Okay, if we graphed the original function and we graphed this new function, they're not going to look the same. They're not the same function, okay? However, they will have the same limit at that value, okay? And so we can evaluate it doing it that way, okay? And it really uses this concept that if f of x equals g of x when x is not equal to a, then the limit as x approaches a of f of x equals the limit of g of x as x approaches a. And that's provided both limits exist. So if they're equal to each other everywhere except at a, okay, where one function is undefined and the other is not, then we can say, okay, we don't care what happens at a, we just want to know what happens close to a. Okay, again, we know that it's undefined at a, but what happens close to it? Okay, that's really what limits are, remember. What is it approaching? Okay, all right, so let's look at this example. Now, this one requires rationalizing the numerator and then simplifying it algebraically. So rationalizing the numerator is really no different than what we did with rationalizing the denominator, okay? We're gonna take, I have this in there, I didn't get rid of them. We're gonna take the top and bottom of this times the same thing, but remember when you're rationalizing, you're taking it times the reciprocal function of that. Not the reciprocal, the conjugate, sorry, the conjugate function. So it's t squared plus 9 plus 3 that we're multiplying the top and bottom by, the square root of t squared plus 9 plus 3. And we have to multiply top and bottom by the same thing, so we're not actually changing the value of it. Okay, so when we do this, well, a square root times a square root, we just get what's underneath, right? So the square root of t squared plus 9 times the square root of t squared plus 9 is t squared plus 9. Okay, and again, remember why we do the conjugate? So the middle terms drop out. So a minus b times a plus b is just a squared minus b squared. So it's minus 9 minus 3 squared. And on the bottom, I just still have my t squared times this quantity, t squared plus 9 plus 3. Okay. So now on the top, I just have t squared. On the bottom, I have that t squared times this quantity. But what happens to the t squareds? They cancel out. Okay. And so I actually have the limit as t approaches 0 of 1 over the square root of t squared plus 9 plus 3. The t squared plus 9, the square root of t squared plus 9? Okay. Yeah, the t kind of looks like a, yeah. Okay, so now look at this. Can I simply substitute in my 0? Will it work? Yeah. So I really just substitute in my 0. It's going to be 0 squared, which is 0 plus 9 plus 3. And so that's 1 over 3 plus 3, which is 1/6. And there's my limit. Okay. So that's called rationalizing the numerator. And you can do that when you have square roots. Okay, and sometimes, especially with piecewise functions, it helps to look at the left and right limits, okay? And so going back to previous result, the limit as x approaches a of f of x is the limit if and only if they are the same from the left and the right, correct? So the two-sided limit exists if and only if the one-sided limits exist and are equal. So when we look at piecewise functions like this, and the absolute value function is really a piecewise function because it's saying if x is positive, our value is just x. But if x is negative, it's actually the negative of x, right? So if I put -2 in, I actually get a +2, which is the negative of a -2. So that's what that's all this piecewise function is saying. It's just breaking that absolute value function into 2 parts and defining them separately. So if we want to prove that the limit as x approaches 0 of the absolute value over x is undefined, we look at both the right hand and the left hand limit. So an undefined, remember we write as this does not exist. You can use that DNE. Sounds like someone's dying out there. Hope not. Okay. Connor, want to check on. Okay, so the limit as x approaches 0 from the right of the absolute value of x over x. What does that equal? Well, if we think about it from the right and think about that piecewise function that we just looked at from the right, that means all of my values that I'm putting in are positive, right? And in other words, just x. So I'm really just saying it's the limit as x approaches 0 from the right of x over x, which is the limit as x approaches 0 from the right of 1. Well, the limit of 1 is 1, right? So I get 1 on that one. That makes sense? Okay, now let's look at the left-hand limit. The limit as x approaches 0 from the left of the absolute value of x over x is really equal to the limit as x approaches 0 from the left of x over negative x, because really the absolute value of x, if my x is negative and if I'm to the left of 0, my x values are negative, right? And up there on that function, it said it's really equal to negative x, right? So this is really negative x over x. And so the limit as x approaches 0 from the left of -1 is -1. Do these match? No. So the right-hand limit is not equal to the left-hand limit. So these two being not equal means that the limit itself does not exist. And, this is what's happening. It's approaching 1 from the right, it's approaching -1 from the left. Okay. So it's, so the actual limit does not exist. And that's how you can prove that it doesn't. Just look at the left and the right. Okay, greatest integer function. So the greatest integer function, again, remember what that does is it takes whatever we put into it and it spits out the greatest integer that is basically to the left of this, okay? So the largest that's less than or equal to what we put in, okay? So to the left of it, less than or equal to what we put in. So let's look at this one. as x approaches 3. So let's look at the left and the right of this. The limit as x approaches 3 from the right of this greatest integer function. Well, let's look at our graph over here. So as x is approaching 3 from the right. So let's go up here to see what happens. As x is approaching 3 from the right, what does it look like your value is going to do? As it gets closer and closer to 3 from the right, what is it approaching? 3. Looks like it's approaching 3, right? It's up here at 3 from the right. But as it approaches from the left, as x approaches 3 from the left of this, so let's go from the left over here. So starting at 2, and we keep getting closer and closer and closer to 3, what does it look like it's approaching? Right before we get to 3, what's my y value? 2. So it's approaching 2 from the left, it's approaching 3 from the right, and that means that this does not exist because your left and right are not equal. Okay, or your right and your left, whichever. Okay, so one-sided limits, it's a good way of showing that the limit does not exist because you can see what happens from the right and left. Even if you have to, do tables of values, so you can see what it does. You can see what it does from the left and the right as it approaches that. Okay, so now a couple rules involving inequalities. So if you have a function f of x that is less than or equal to g of x, when x is near a and the limits of f and g both exist, then the limit as x approaches a of f of x is also going to be less than or equal to the limit as x approaches a of g of x. Okay. And so, yeah, it just follows through that if one function is less than or equal to the other, the limit as they approach the same thing is also going to be less than or equal to it. Okay, and then we have what's called the squeeze theorem. And this is saying that it's between. So it kind of follows from that. If it's less than it, right, it's going to be less than it. Well, if I have it between two things, so in other words, if I have a function between two other functions, when x is near a, then the limit as x approaches a of f of x is going to equal the limit as x approaches a of h of x is going to equal L, then the limit as x approaches a of g of x is also going to be L. So if the outside two ones approach L, approach the same thing, the inside one's going to also. It's called the squeeze theorem. Okay, and this is kind of what it's looking like. It's just saying that, if G is caught between F and H, it's forced to have the same limit at x equals A. Okay, so this is kind of what it looks like here. So a classic example of this, the limit as x approaches 0 of x squared times sine of 1 over x. It's going to equal 0. Well, this is why. Okay, we can't apply the product rule since the sine of 1 over x, well, 1 over 0, we can't divide by 0, right? It does not exist, so we can't just do the product rule. But we know that the sine of anything is between -1 and 1, right? It vacillates between -1 and 1. So we know that's true. And if we take that inequality and we simply multiply each of these by x squared, so I multiply -1 by x squared, it's negative x squared, multiply this one by x squared, that's what it is, multiply this one by x squared, well, then I have what I'm looking at. Okay, so I know that because this one's between -1 and 1, multiplied by x squared, this one has to be between negative x squared and x squared. Okay, so here's my graph of y equals x squared, here's my graph of y equals negative x squared. Notice what's happening as it approaches 0. It gets squeezed in there. That's why it's called the squeeze theorem. Okay, it gets squeezed down to what it's approaching for each of these separately. Okay, so our function y equals x squared and our function y equals negative x squared both approach 0 at 0, don't they? Well, the same thing's going to happen then for my graph of x squared times sine of 1 over x. Okay, And this that you see up here in the middle, that is the graph of x squared times sine of 1 over x. Okay, and it does get squeezed down. That has to stay between that x squared and the negative x squared, because sine has to stay between -1 and 1. That makes sense? So it's going to have the same limit. It's squeezed down to the same thing, that 0, 0. So this limit is equal to 0. And many of these squeeze functions do have trig functions as part of the function part of it, because we know that sine and cosine both oscillate between -1 and 1. And so we get whatever we have multiplied that by, we get that inequality, and so it's going to be squeezed between those. And that allows you to find the given function as a multiple of the trig function, like we did there. Okay, so that is your assignment. You can go ahead and get busy working on that. We will have a quiz tomorrow over these first 3 sections. So we'll go over these problems first, and then we'll have the quiz. It will be a short quiz.